1564 to 1642 AD. Galileo Galilei, and he was an experimentalist. A new brand of scientist, the modern scientist. You could argue he was the first scientist, at least as we define a scientist in the modern day. His idea of science, and the previous idea of science, if it was even called that, very different. Before Galileo, if you're a scientist, if you're an academic, your job is not to create new knowledge. It's very much not your job. Anything worth knowing was figured out in ancient times. It's your job to carry that knowledge to the next generation without adding to it or taking from it or screwing it up in any way. That was the job of the academics, of the scholars of that time, of the scientists. Galileo's idea of science is very different. It's basically what we now call the scientific method. It is if you have a hypothesis, for it to be a scientific hypothesis, it must be testable. You can speculate all sorts of things. If you can't come up with a way to test your speculation, it's nothing worthy of the time of a scientist. But if you have an idea and it's testable, a testable hypothesis, you then go out and you make a test. You make an experiment. And if it fails the test, your idea is wrong. If it passes the test, your idea is not necessarily right. That's the thing that people don't understand about science. We don't prove anything to be right. All that we have the capability of doing with the scientific method is proving things to be wrong. Now, if an idea passes the test, then it lives another day, and people will dream up other tests. And if it passes test after test after test, we gain confidence in it. We might begin to start thinking of it as close to truth, or maybe even as truth, but we can't prove anything to be truth. The scientific method is a way of weeding out bad ideas so the good ones are left standing. So it's not perfect way to come up with truth by any means, but it's done pretty well. I mean, we have all this technology around us, sitting on your laps and everywhere. This is all because of this practice of weeding out bad ideas. It also makes science, this is an aside, but a very interesting and sometimes difficult field to work in. Our job is to prove all of our friends and colleagues wrong. And that's what we do. We write these papers. Some people will be bold and throw an idea out there. And then you have everyone else who comes in and they try to attack it, even if they're your friend. That's what I do too. And my friend puts out an idea, and it's my job to take them down. And we'll go to conferences. You might think of scientific conferences as these orderly events where someone goes up and says blah, 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 and everyone nods in agreement because we're all scientists and we all know truth. But no, it's not like that at all. Someone goes and says an idea, all the hands go up. It's now our turn to try to take this person down in front of everybody else. And we're humans, Egos are at stake. A couple things. It makes it difficult. We all have our egos, and we don't like to be proven wrong. And there's funding. There's only so much funding to go around. If you put out idea after idea that people shoot down, no one's going to give you any money. So if you put out idea after idea that stands the test of time, you do get money. So it's a high-stakes game where careers are on the line. So it can get nasty. And it does get nasty, particularly when you're working at the cutting edge. Often that's kind of brushed under the mat. By the time we actually make a discovery, that's all kind of hidden. And we put a sterilized, cleaned up version out there for the general public to read. But whenever you read a scientific result, usually there's a lot of crap that went into coming up to it. But anyway, total aside, that's kind of fun to think about. Okay, Galileo was the first experimentalist. Anyway, he's an experimentalist. He did many different experiments, but the one he's most famous for is taking a telescope and pointing it at the sky. Now, he did not invent the telescope. That's a common misconception. They were invented before this, probably for military reasons. If you can see your enemy coming at you from farther out, you have more time to prepare your defense. And so it's a very useful military tool, but no one thought to point it up at the sky until Galileo did, and immediately he had 4 revolutionary discoveries. All these kind of changed the game. We'll start with kind of the easier ones first. So, depending on which textbook you look at, that's Galileo. I threw that in there. My dad's a newspaper editor. I spent a lot of time in composition rooms when that used to be done manually. I used to do some of that when I was younger. One thing I've learned about textbooks, newspapers, they'll flip photos. It's bad if you have a photo of a face and the face is looking away from the text. It makes it seem like even the pictures aren't interested in reading this thing. And so if you look carefully, you'll notice that maybe about 20% of photos, and maybe that's an exaggeration, I don't know, but something like that, 10-20%, are actually flipped in textbooks. Anyway, I think it is indeed flipped in your textbook. Okay, so first one, lunar features. Natural thing to look at. He has this telescope, he points it at the moon. And he realized that the moon is not a smooth object. Now, even with the naked eye, you can see there are dark patches and light patches. And here's kind of this is actually an impossible picture of the moon to take. I'll explain that in a second. But you have these dark regions that we call maria. Maria means sea. People thought that maybe these were oceans of some type, but really just a darker form of rock, darker color of rock. And then you have the light areas, which are the highlands, the lunar highlands. The reason you can't get this picture, if you look at this picture carefully, you see there's like a row of craters here. And you don't see craters over here and over here. In these regions, it looks perfectly smooth. And that has to do with the illumination. If you look at the moon through a telescope, you'll always see the craters on the terminator, the division between the light part and the dark part. That's because right there at the terminator, the light's coming in at a glancing angle. If you're standing on the moon, right at sunrise or sunset, right on that terminator, the light's coming in real shallow, and it will cast big shadows from the mountains and the craters. So what this is actually two pictures. One, first quarter with the sun on that side looking this way, the other third quarter with the sun on this side looking that way. And so both of these were taken when the terminator was running up and down the middle. So that's where you get the shadows cast, and that's why you can actually see the three-dimensionality. I know, it's a tangent. I like this picture, but I feel like I have to explain it, because if you look at the moon, it will never look this way. Anyway, does that make sense? See what I'm saying? Okay, it doesn't really matter for the point of the lesson. But Galileo looked, and he saw the craters. And what the church had been teaching, it's not really a statement about the geocentric model or the heliocentric model, but it maybe has its origin going all the way back to Aristotle and Plato about these ideas of what is considered perfect or ideal in the universe. And it was taught, the church taught that the moon was a perfect sphere, perfectly smooth. Now everyone had to acknowledge it had blotches on it, dark regions, light regions, but part of church teaching was it was a perfectly smooth object. Galileo looked up at his telescope and looked at the terminator, the division between day and night, dark and light on the moon, and he saw the craters, because he saw the shadows being cast. He could see the mountains. He could see that it was not a perfectly smooth object, and this contradicted church teachings. The second discovery, he pointed it at the sun. And similar thing, it doesn't really test the geocentric model or the heliocentric model, but for centuries the church had been teaching the sun is also a perfect object, not just perfect in being a smooth spherical object like they had taught with the moon, but an unblemished object. The moon was blemished, clearly. We see that when we look up. The sun was unblemished. And he looked up at this telescope and he saw sunspots. Yeah, now, I don't know, if I stare at the sun through a telescope, I'm sure I'm going to be seeing spots too, but he documented it pretty carefully, and there are blemishes on the surface of the sun, so this was a problem for the church teachings as well. Okay, now into the ones that relate more to the geocentric and heliocentric. The next one is his most famous discovery, but not his most important, I would argue, and that is Jupiter's moons. For the first time in all of history, a person looked up at the sky and discovered new worlds. And if you think about it, it's kind of remarkable. Nowadays we discover them all the time. We've discovered 500 planets around other stars just over the past decade or so. It's pretty common for us to discover new worlds. We discover new asteroids and objects out around Pluto all the time now, but that had never been done before. No new worlds, no new moons. He looked at Jupiter, and these are his actual observations. He had a date on the left. I
think it was like December, January 7th, 8th, 10th, 11th. And he's noticing these stars right around Jupiter, points of light, and not really stars, he didn't know that, and he drew them, and they were changing from day to day, dancing around Jupiter. Eventually he realized they weren't distant stars, with Jupiter sitting in front. They're actual objects orbiting Jupiter. Like in the geocentric model, everything orbits Earth. In the heliocentric model, things orbit the Sun. Here's something orbiting Jupiter, and that's a real problem in the geocentric model. In the heliocentric model, you still had the moon going around the Earth. You could, everything didn't have to orbit that central object. But in the geocentric model, it's important that everything orbits Earth, because Earth is the most important thing in the universe. Of course, everything would go around it. And here he just discovered 4 worlds orbiting something that's not Earth. So a big problem for the geocentric model, which is, again, a problem for the church. Let's see, I think I have a little movie here. So if you take the lab course, by the time we get up to lab 3, you can pick Jupiter, Saturn, Uranus, Neptune. It doesn't matter, any of those worlds out there with moons, but Neptune only has one that we can really see. And you take like an image every day. Here's just a snippet from a few semesters ago, Jupiter. Now, in this picture here, Jupiter is really kind of... The problem is you can't see the clouds on Jupiter and the moons at the same time. And the moons are so faint, you have to kind of overexpose Jupiter to see the moons. So you pick one or the other. Here we picked it so you can see the moons. I'll just play a handful of images. Clearly they're moving around the planet. So if you're taking a lab course, you'll be making your own such movie. Okay. Venus. This is what I think is the most important. It's also the least known of his 4 major discoveries, and it's the Venusian phases. Phases of Venus. We're just talking about different hypotheses, making different predictions, and go out and test them. Those that fail the test are wrong. Those that pass might be right. Well, we have 2 models. We have the geocentric model of Ptolemy, and we have the heliocentric model. So let's consider and they make different predictions for the phases of Venus. That's the point. So here's the geocentric model. What we have are Venus's deferent, and then out beyond it, the Sun's deferent. And riding on Venus's deferent is Venus's epicycle. The whole thing fits between the Earth and the Sun. The Sun is moving at a uniform rate, so it doesn't require an epicycle, or if it has an epicycle, it's super, super, super small. But Venus has this big epicycle here. And here we've put together a bunch of configurations with, here I'll come back over here so I can point to the mouse. Here we start with a new Venus, where Venus is between the Sun and the Earth. There might be a little bit of light over the top if there's a tilt in the orbit, but it's essentially new. And as you move over here, you get to a crescent. And here you get the kind of as much illumination as you're going to get coming from the Sun over here. As you work your way back around, Venus isn't going on the other side of the Sun. It's still between the Sun and the Earth. So you go back to a new phase. Come out here, you get a crescent again, but then it goes back to a new. So in the geocentric model, you never get a quarter Venus or a gibbous Venus. It's always crescent or new. That's the prediction. I mean, Ptolemy didn't make the prediction. He made the model. If you look at the model carefully, this is what has to be if it's correct. Here's the heliocentric model, where Venus and Earth are both going around the Sun. Sun's at the center. And here a bunch of different configurations put together. Again, Venus between the Sun and the Earth. You have a new Venus, except maybe a little bit of light over the top or the bottom. If Venus's orbit's tipped with respect to the Sun-Earth orbit, as it moves around, you get crescent. Eventually a quarter Venus, gibbous, and then you get a full Venus. When Venus is on the other side of the Sun, it's being fully illuminated on the side that's facing us. Of course, it's hard to see because the Sun is right, very close in the sky, but you would see it approach full, and then it appears in the morning sky or the other sky, waning back down to new. You get the full phase cycle like the Moon in the heliocentric model. Well, you can't see this with the naked eye, but with Galileo's telescope, very early, very crude telescope. I have some replicas made, not in terms of the body of the telescope. I just use PVC pipe, but the optics are the same optics that Galileo used. I have them over at the lab. If you go over there for the introduction to lab course or for office hours, You might want to look through them. They're really hard to use. It's amazing that he could see this stuff, but he did see it. And this is what he saw. These aren't his drawings. These are modern-day images. But you have new Venus, a little bit on the top because there is a tilt in the plane, going to crescent, quarter, gibbous, and full. And you also see the size change, which makes sense. It's not just you get the full phase cycle, but size changes. And Venus will be biggest when it's closest, that's new, and smallest when it's farthest away, and that's full. And this is exactly what we see. It matches the prediction of the heliocentric model perfectly. It's in contradiction to the geocentric model. So this is the end of the geocentric model. I mean, it should have been the end of the geocentric model. Okay, so Galileo made these observations in 1609 and published them in 1610, 400 years ago this year, back in March of this year. And he published this book called The Starry Messenger, which of course is referring to himself, part of his big ego. It got him into trouble. But these are certainly worth publishing. And there's kind of the title page of the book. And what this book does is it very aggressively challenges both religion, at least of that time, and science of that time. Because as I said, he's the first modern scientist. Well, who were the other scientists? Well, the other scientists, they're academics in various institutions of learning. But the role of the academic, I don't want to say the role of scientists because I don't consider them scientists, but back then the role of the scientist or the academic was not to create new knowledge, certainly not to challenge existing knowledge. Their job was to pass it on without messing it up into passing it on. To teach what the ancients figured out, because they pretty much figured that if there's anything that can be figured out, the ancients figured it out, and it's just their job to pass the knowledge on without getting it wrong. And so he's not just challenging religion, he's challenging the people who might be his allies, the academics, the intellectuals. He's just challenging everybody, not just in his book, but he'd go and give talks and he'd publicly ridicule Aristotelians, people following the geocentric model and their ideas. He was harsh to them. He would make fun of them publicly with them present. So he didn't win very many friends that way.
But he figured he'd be okay because the results are the results. And he saw it with his own eyes, the phases of Venus, the moon's going around Jupiter. And so time would bear him out as correct. But he immediately ran into problems. People had a very hard time replicating his results. One, because there weren't very many telescopes, right? Kind of a new invention. Usually they're poor quality. So he started making telescopes and sending them around to all the important people, the kings and dukes and whatnot, sending them out off to all these royal courts, and they'd come with messages saying, look at Jupiter, look at Venus through this. And there's story after story of royalty getting these things and holding it up to the sky, half the time backwards, half the time when it's cloudy, half the time during the day. And these things are really hard to use. I have a replica of Galileo's telescope that we made. Not like historic replica, it's made out of PVC, but the optics are exactly the same optics that he used. Higher quality because you can just order them these days. And I looked at that thing and it's really hard to see. Things are blurry on the edges, clear in the middle. But it's hard to just find anything in the sky. I don't think I've ever actually looked at Jupiter with it, because it's just hard to find which star. Very difficult to use, and with people not really understanding it, and not just not understanding the instrument, but not understanding how to use science, how to verify a result, how to be patient, how to record what you're seeing. All the royalty, they just kind of gave up and dismissed his ideas. They could not replicate it. The problem was there are no other scientists out there. He was the only scientist by the modern standard. So his results, although presented in Starry Messenger, were hard to replicate. So he just spent all this time going around writing this book, giving talks, being a bit of an ass, and no one seems to be able to come up with his results. And the church got tired of it pretty quickly. Well, actually, he got about 6 years. In 1616, was banned by the church. So Copernicus' book wasn't banned for like 73 years. Galileo got his book banned in 6 years. And the church Pope at the time told him to cease and desist, stop this nonsense, and he did. But then there was a new Pope. Pope Urban VIII. And Urban VIII wasn't exactly a friend of Galileo's, but an acquaintance. He was familiar with the Medici family, who were the sponsors of Galileo. Galileo worked for the Medici family. And Galileo thought, well, you know, we have this kind of relationship. We know the same people. Maybe the Pope will hear me out. And so he requested an audience. And the audience was granted. He went and had a discussion with Pope Urban VIII. He said, okay, I know when I wrote my first book, I was really aggressive, pushing these ideas that contradict church teaching. Give me a second chance. Let me sit down, let me write, to use kind of a modern phrase, a fair and balanced account. And he followed that kind of in the modern context, in the sense that fair and balanced isn't necessarily fair and balanced. But Urban VIII said, yeah, you can write a book. You can present both sides, the geocentric side and the heliocentric side. But in the end, you have to come to the conclusion that the geocentric model is right. Because who are we, mere mortals, to know the mind of God, or to question the word of God? I'm paraphrasing, but that was essentially the argument. And Galileo, not having any other choice, said he accepted the terms. He'd write a book that presented both sides, but came to that conclusion in the end. And off he went, and the Vatican wasn't too concerned because they figured it'd be a fairly academic treatise, lots of equations and math and stuff, and no one would really pay too much attention to it. Instead, Galileo, instead of writing kind of a dry academic work, he wrote the dialogue. So here's the full title, Dialogue Concerning the Two Chief World Systems. It was not an academic text. It was a narrative, a debate between fictional characters, and rather entertaining. He didn't write it for a few academics, he wrote it for the masses. And he wrote it in a way that they would want to read it and to be entertained and excited about it. And this came out in 1632. So this is 16 years after his first book was banned. He waited for his big chance, and this was it. Now, he had to present both sides. It wasn't like half the book was one side and half the book was the other side. He had two main characters, and they each took a different side, and they debated the pluses and minuses of their models. The heliocentric model was presented and argued for by a character called Salviati. The geocentric model was argued for by a character called Simplicio. Simpleton. Again, not necessarily a fair and balanced presentation of the two cases here. And if you read through the book, appropriately translated, the heliocentric model is presented as the better argument, because it is the better argument. Galileo had the observations. He had seen it with his own eyes. He just knew that it was correct. And it's hard to present something that's correct on equal footing with something that's not correct. But, so he did his best, or he did as he intended to do, and the heliocentric model was presented kind of as the better argument. But to balance that out, he gave Simplicio the final word in the book. And he ends the book by saying, all of this is kind of nonsense and shouldn't be taken too seriously, because who are mere mortals to know the mind of God? Who are mere humans to question the word of God? Sound familiar? Again, I'm paraphrasing, but what Galileo did is he took the words that the Pope had uttered to him on that day and put them in the mouth of this character whose name is Simpleton in a book written for the general public. Not the smartest choice here. So Simplicio got the final word, but it was the Pope's words. Salviati, as I said, had the better argument. Well, one other thing with the dialogue. It was not written in Latin, like Copernicus's book. Latin can only be read by a few. He wrote the thing in Italian. Now, literacy was not widespread, Italian. But anyone who could read Italian. So again, he's marketing it to a different group of people than just the academics. And then, of course, the shit hit the fan. The book came out in 1632. In 1632, he was called before the Inquisition. He didn't want to go to the Inquisition. He kind of hid in his house until 1633, when his friends encouraged him, "You better get there. This is not going to end well for you if you don't show up." So he went to the Inquisition. I think I got a famous painting of that here. There he is before the Inquisition. And they told him he had to do a couple things. First, he had to denounce his writings, which he did, and house arrest until death, which he also accepted. So he kind of got off easy. He got to go home. He just couldn't leave his home. You know, people would bring him food. He'd write with his daughter. There's a nice book out called Galileo's Daughter, where he has communications with his daughter, who's a nun at this point. And just kind of slowly went blind until he died. And that was the end of Galileo. That's the story of Galileo. Kind of sad, kind of depressing. Now, the church, of course, is an institution of forgiveness. And after a certain amount of time, they forgave Galileo's crimes. Anyone know when that occurred? 1992. So, slow-moving institution, the church is. So, at this point in time, they said, yeah, Galileo was right. But I don't mean to pick on the Catholic Church. That's not really... I'm picking on them historically. A lot of people don't realize it, but the modern-day Catholic Church is a pretty lenient entity in terms of science. Every year, maybe it's every other year, they host the most prominent conference on theoretical cosmology. The world's experts come and discuss and debate the Big Bang Theory right there at the Vatican. And the Big Bang Theory is accepted by the Catholic Church. I mean, they, of course, say God created the universe, but this is the mechanism of God's creation. So they accept the Big Bang Theory. Catholic Church even accepts evolution, which in scientific circles is as close to fact as, like, theory of gravity is close to fact, but, of course, debated from religion to religion. So the Catholic Church, I think, learned a few things with the experience with Galileo, and they're pretty accepting of modern scientific results. All right. Questions about Galileo?